Cool. All right. This jacket is actually quite hot. I'm going to take this off. So I thought this would be a good idea, but I am boiling in this thing. Okay. So I'm here to tell you. Actually, no, I'm going to leave this on because it's cool. Okay. In 2010, 10 years ago, I was founding a company called Nodejitsu, and it was kind of a Heroku for Node.js, platform as a service. And over the past decade, there's been a lot of things like it, but better. And infrastructure as a service and platform as a service, and the products built on them, they've become unsustainably complex. And the cloud is, and I say this as a veteran of DevOps, that it's a house of cards. And what's worse is that as builders of the web, we've found ourselves in a landlord-tenant relationship. But all of that is changing because we've entered a new era of ubiquitous computing, and we've seen a proliferation of hardware and data. And today I want to talk about why this is pushing storage and compute from the cloud towards a network of peer-to-peer. And because this isn't a prediction talk, I'm actually going to show you a framework. I'm actually going to show you a new runtime. And I'm also, by the way, not the first person to have this perspective. Peter Levine from Andreessen Horowitz did a really great talk entitled The End of Cloud Computing in 2016. And then in 2019, he doubled down on this thesis, delivering a really great keynote at the A16Z Summit. So here we go. All right, so computing, what drives us toward or away from decentralization or from centralization? In the beginning, everything was centralized, right? And they were centralized for a reason. Computers were the size of a room. And the upside was that a few million people were computing. But the downside was that a few million people is relatively few people. But clearly there was a demand, so the cost of microprocessors went down, and we had the personal computing revolution. Hardware sales boomed, and suddenly 2 billion people were computing. And this was good. This was great. People were very happy. Hardware sales boomed, but there was a new problem, which was that sharing data was really difficult. Okay? So we took a swing back towards centralization. It was distributed, but it was highly asymmetrical. Right? Somebody said basically, okay, I'll plug in a computer, I'll turn it on, I'll make sure it's always on, we'll call it a server, you can pay me to access it, and it'll be a hub. And the upside to this was that we figured out a pretty reasonably good way to share data. It was intuitive and it made sense. And then information access sales boomed, right? You had AOL, you had companies like this that were all about information access and selling it to you. The problem was that there was growth, right? This was the .com era, right? And everything was booming, but servers were the bottlenecks. Right? So we took a swing back to decentralization, to peer-to-peer. This is the peer-to-peer era, the 2000s. And this was really caused by this quest to find protocols that scaled. Right? You had limitless access that scaled really well. Millions of people were sharing petabytes of data. Peer-to-peer proved itself as a very robust and great protocol. Infamous products like Napster, Nutella Network, BitTorrent, all of these things became household names, right? But the problem is that it's the 80-20 power rule kind of applies here, right? 80% of peer-to-peer model is very hard to wrap your head around, right? Versus client server. And sure, once you get to that 20%, it scales really well. It's easy to maintain, but all of this was tribal knowledge, right? And this is the pre-GitHub era, so very few people knew how peer-to-peer worked. Copyright holders were also extremely upset. Users expected everything to be free. Everybody was panicking. Nobody knew how to get anybody to pay for anything. And so we found ourselves taking a hard swing back to centralization. And this is really where we have peak cloud computing. Cloud platforms like AWS enabled people to build things like they couldn't before. Nobody had data centers. Nobody knew how to do this correctly. And Amazon said, OK, we'll rent you the infrastructure, and we'll handle the hard parts for a price. And Amazon did really well at this and entrenched everybody. And half the internet or more is built on AWS. And everything became a service. So here we are in the era of everything as a service. The upside is that improved UX and subscription-based access, which investors love, made it possible to ask users for money again. We'll give you all the content in the world for only $10 a month. And copyright holders are really happy with this. Man-in-the-middle business is booming. The problem here is that DevOps has become insane. And DevOps is it's a house of cards, this whole situation. And worst of all, like I said, it's really a rent extracting model. Everybody's dependent on the cloud. But there's something taking us back very quickly to decentralization. And that thing is, we want computing everywhere. We find a use case for computing in almost every corner of our lives, right? And because of that, we're seeing a proliferation of hardware and data. We're entering the era of ubiquitous computing. OK, controversy. How do we compare AWS to all this hardware that we're surrounded by suddenly? Well, you can't really compare it specifically. There's some nuances to how you compare it. It's not a one-to-one relationship. The desire for ubiquitous computing has driven this hardware proliferation, but we need to put it into perspective as technologists trying to find utility in it, right? So today, there's about 7 billion people in the world, and there's about 15 billion mobile devices. And that doesn't count 2.5 billion laptops and the countless IoT devices that exist. We're just talking about mobile devices here. So let's look at AWS. So AWS has about 38 data centers in 87 availability zones, 27 regions. And James Hamilton said most Amazon data centers house between 50,000 and 80,000 servers, so that's about 3 million servers. And so clearly, there's more hardware outside the data center than in any data center combined. But how is it fair to compare any of this? I mean, AWS services, they're always on, mostly always on. They're really robust servers. So the only way that you compare this is, on average, the individual hardware is unreliable. It's online less frequently, and it's statistically less powerful. People have different battery levels. People have different security settings. We consider all of this hardware unreliable. But individually, a device doesn't replace a server. It doesn't run down battery, acting like a server, and it doesn't run up CPU acting like a server. Instead, individual devices make small contributions that constitute a larger, more robust network. And of course, all of this hardware proliferation is an opportunity, and it's leading to data proliferation. Basically, we're creating an insane amount of data, and it just gets more insane. The velocity and the volume of data creation and consumption is a big driver back towards decentralization. So you probably heard, the self-driving car generates 10 gigabytes per mile, and some cameras generate 300 gigabytes of data per second. Sensors are popping up everywhere, right? There's sensors in everything. And almost everything in the world is generating some data about the world around it. And then we want to do something with that data. We want to do something with that data close to where it's being actually created. So we want to create, process, and replicate that data as close to possible to where it's being created. But a good example is a self-driving car doesn't want to send data all the way back to the data center to avoid a potential obstacle. Zero latency is affordable in that case. Medical data should stay private on premise in a hospital. Hospitals should be able to connect directly to each other. A lot of pressure can be taken off, for example, Uber's servers if the rider can connect directly to the driver, right? So this stuff is pretty obvious, but the question is like, how is it possible? So round trips to the data center make less and less sense. But another driver that's really important, that's something that's driving us towards decentralization, is the cost and the complexity of building services, cloud services, and building on top of infrastructure as a service and platform as a service. Growth. So as your application grows, as you have demand, engineers end up bending over backwards to accommodate this. And the fact is that a cloud gets more expensive, more complex, and less reliable with growth. That's a fact. And I don't think there's anyone here that would agree with that or disagree with that. Peer-to-peer gets less expensive, maintains the same complexity. And of course, it becomes more reliable as your network grows. So a lot of companies are seeing peer-to-peer as a potential for supplementing their existing infrastructure or escaping it entirely in some cases. So we saw these key drivers that are pointing us towards decentralization, and that's hardware proliferation, data proliferation, and cost complexity. And this is really what's going to drive the next decade of computing, and this is going to be what we spend our time solving problems for. So we started a company to solve some of these problems. We're early, kind of like we were early to Node, like we were early to the web, like we were early to all these other things. We make it possible for the average developer to build peer-to-peer apps using HTML, CSS, and JavaScript. And then also provide tools to help with that at scale. What we were looking for was a fundamental improvement. I think that, for example, in the JavaScript space, there's a lot of competition for fast servers. They're all incremental improvements of each other. We call this horizontal progress. Right? All these solutions are racing to be slightly faster or maybe ergonomically better. But what if apps could just communicate directly to each other? Better and faster servers really kind of lose their meaning, and they become less important as we have more direct transactions between applications. So with peer-to-peer, the responsibility becomes distributed. And users own the hardware, and they take a degree of responsibility for participating in the network, storage, compute, network connectivity. And so what we want, really, is to just remove as much of the cloud as possible without sacrificing any performance or reliability or security. And in order to do this, we realized what we needed was a new runtime. So servers are ideal for supercomputing tasks, and browsers are great exclusively for client-server apps. And there's a lot of reasons why they're not great for building software. But Snyk is a runtime that is for distributed web apps, so native apps built with the web stack. And it provides things that the browser just can't or won't, right? So local first capabilities, right? We want Bluetooth. We want to not have to use internet for adjacent devices. So peer-to-peer makes sense, but how do we unlock its potential? What does this runtime look like? I'm probably preaching to the choir when I say this, but obviously it makes sense to be aligned with the web here. The web has the largest, most active community, the best documentation, biggest backers, easiest to staff for. well enough patterns, well-known patterns that it's easy to iterate really quickly building software, and much easier than a lot of other platforms may be. Okay, so what does this look like? Well, this is about as simple as it could get. So you can write some HTML, you can write some JavaScript, you can run the build tool, and it will encapsulate your code in the runtime, and then it'll build it for mobile or desktop. And you can bring your front-end development framework, the one you like the best, React or Vue or Preact or Svelte or whatever people are building with today or tomorrow. That's about as simple as it gets. So I guess the question that probably a lot of people are saying when they see this is like, well, this is kind of like something I've seen, a little bit like something I've seen. And the question is, why not Electron? Why not Phonegap? Well, obvious reasons. Phonegap only runs on mobile. It's also ancient. Electron has quite a few valid criticisms about its distribution size and its memory footprint. Our binaries for desktop clock in at, or weigh in at about 1.5 megabytes. And that's it. And on iOS, I think we're building at about 13 megabytes, and on Android about the same, less actually. So some of the things that we wanted to do, of course, was run on all the major desktop platforms, but also the mobile platforms. We wanted to build in packaging. Packaging for Electron is like got too many options, and it just doesn't make any sense. We also wanted to make the backend optional, and we can because we're exposing these APIs like file system in the browser, polyfilling the APIs that don't exist yet or we don't think do the job. And then we also expose UDP and Bluetooth, so you get these peer-to-peer and local first capabilities. And JavaScript Node developers will feel right at home here because our APIs are almost, they're compatible. So the other thing was like, okay, so we built this runtime that allows you to build cross-platform native applications using the web stack. This is very cool. Did we have to boil the ocean and also build the peer-to-peer libraries on top of it? Well, there's some other peer-to-peer libraries that exist, and they have some reliability concerns, and we realized that when we were testing them, because we can't go to customers and say, hey, replace some of your cloud or all of it with something that we can't quantifiably, with empirical evidence, make claims to. So what we decided was that we needed to have a specification, and it needed to be informal and it needed to be formal. So I think a specification separates hobbyists from scientists. And personally, I'd rather debug a couple hundred lines of a specification than a couple 100,000 lines of a distributed system that is incredibly difficult to reason about. And passing tests and GitHub stars and all of that kind of stuff, it really doesn't matter unless you have a specification that can be proved. So take a detour really quick. And I'm going to put my browser over here, and I'm going to go to this document. So my co-founder, Dominic Tarr, and I have been writing this specification, and it's for NAT traversal. And so some of you may or may not know what NAT traversal is, but it's essentially the most important part of connecting peers together in a peer-to-peer network. And I think that it's time. Where is it? Oh my God. Change visibility? Should I do it? Oh, I have to type it out. What's it called? Oh, good idea. We have a we have a Stack Overflow user in here. Okay. Okay, maybe that's it. Okay, I can't see it on my screen over here, so. Oh, it's not going to let me paste? Oh, it is. Okay. Oh. Okay, we can do this.
Also, is make private not public.
Oh. This is what we want. Paste. Okay. Luckily, we have this ability too. Visibility is already public. Okay. Okay, so that's a NAT traversal spec. Okay, now we still have some other things here. Okay, so okay, so that's a spec. So we want a spec. Now that's the informal spec. So what we've been doing is we've been working on the formally verifiable part. So if anybody's familiar with TLA+, that's what we're working on right now. It gives you a way to mathematically, formally verify the states of things. So I have an initial state, and I have following states, and all those states can be enumerated, and then you can have a deterministic distributed system. And that's really important, because the cloud isn't deterministic or formally verifiable, because it's all private. We don't know what it does. Okay, so that's the NAT traversal spec. So the internal kind of high-level overview of the runtime is that we take libuv, right now just a small subset of libuv to do these basic things that we need to do like UDP. And we bridge that to the operating system component called the WebView. WebView historically wasn't very consistent, but now it is. And so this allows you to basically get exactly the same rendering across all of the platforms. And gives you these nice primitives like a correct file system access and a complete networking stack. So like I said, all of the APIs are really quite inspired by Node. In fact, pretty much compatible. And I just want to briefly, before I run out of time, I have 2 minutes, talk about security. So Electron, bad idea. Node and HTML went sandbox. So what we're trying to do is bring together the best parts of the security of the web and combine that with the best parts of the security of the desktop. And the capabilities of the desktop and mobile. So sandboxing is super important. And then obviously there's some things to follow along, to not be, to not make some big mistakes. And we have guides on the documentation here. So there's guides over here for building things. And then really quickly, I want to try to just show. Here's my terminal, but I won't be able to look at it, so I'll have to kind of, here's the code. You know what? Let's open source it. Okay. Okay, that's not the right one. We want this one. Socket. Okay. So here it is. It's in alpha, but I think it's ready. No more really significantly big changes. We're going to make it public, and we're going to copy and paste this. Okay. It's open source. All right. So I have 14 seconds left. Okay. Well, if anybody wants, I'm going to do demos for each and every single one of you. I'm going to show you how to use it if you're interested. So come and find me, and We'll build peer-to-peer apps, and we'll escape the tyranny of the cloud. Thank you.